Any questions?
So just so I can remember the definition, I guess, of unitary and orthogonal?
Excellent question. Orthogonal. I have this pen, and I'm holding it at 45 degrees in my laptop coordinate system. And I turn it around, and now all the data I collect about the pen looks totally different. All the pixels have gotten mixed up if I'm taking the video, but it's still the same pen. And I know it's the same pen because it has the same length. So orthogonal transformations leave lengths invariant, which is if I have a vector x and I multiply it by its transpose, that's length square, which up or down just means I'm looking at transpose or not. We ask ourselves, what a linear transformation, can I take the original components and add them up in some way to get the new orientation of the pen? So I say, let me look at rotated by a matrix R. So now if it's the same pen, I must have that X transpose X prime prime, the new guy, which is the X transpose R transpose, because when you take a vector matrix or two matrices, you get them transposed in the opposite order times, the original guy rotated. So that's what the new length is. So that says that X times a matrix product transpose times R should be the same no matter what x's are, which means that rotation transpose R equals 1. So this is called an orthogonal transformation. If you take determinant of both sides, you obviously get the determinant must be plus or minus 1. Well, I'll just do it. Determinant R transpose R equals determinant 1. Just take two sides. We know determinants multiply, so determinant of R transpose, determinant of R this is number 1. When you look at determinant, you realize that transpose doesn't change the value of determinant, so we get the determinant of R square must be 1. So that's an orthogonal transformation. Now, if determinant of R is 1 and not minus 1, that's called proper orthogonal. And that has to do with, what we study in determinant. So for example, in 2 dimensions, determinant is area between its two vectors that define the edges of parallelogram. And, if you rotate this, nothing happens. But if you invert the order of them, you can get the same area with the minus sign. So that's what the other minus is doing. So you have to distinguish the two cases. So that's orthogonal. And the main thing is that the transpose is the inverse, unitary. Same story, but now we have a Hermitian transpose where we take the whole vector and take complex conjugate of each component. We multiply with the original thing. And we find R square. Well, let's call it R square. Because if we wrote the original number x, all the x's, in the form R e to the I phi, then in this product, we just get a sum of Ri square, which is the length square in complex plane. So the complex number has its magnitude and its phase, and we only want to preserve the strength of that complex number, the power, this number. And that's why we look at unitary transformations. So then you go through the whole business and you find out the unitary transformation, everything is the same except you have Hermitian conjugates. Hermitian conjugate is a transpose plus complex conjugation. Are you happy?
Yeah. One quick thing about orthogonal matrices, I heard that I believe it's if the magnitude of all the columns sums to 1. Is that an equivalent definition?
You're right. And, you can just check it by hand, but it is the same thing. So that way of thinking is helpful often when people think of probabilities and stuff like that. Okay. I like this geometrical intuition. I really think of all these things as rotation in d-dimensional real or complex space.